Last time they didn't have a long enough crane, and then the weather was bad, and now we don't know. But we have a different room for the midterm, so you will not be cooked, at least not by temperature, sheer temperature. Okay, well, good afternoon, welcome to 240. So, well, what's new? I guess you know that the homework is due, and I will announce a new one. That new homework will be then the last one we will have before the midterm. I will announce. I mean, it will be, yeah, it will be all the material through and including what is in that last homework. And I'll be a little bit more specific in one of the next lectures.
A quick question on the midterm: is it possible to get some old midterms or something?
Yes, actually, if you are within ECS, you can access all the previous sites of 240, but I will also post a couple of old midterm exams. So. Okay, we've talked about transconductance amplifiers, and in particular we looked at the common source stage as an example, and looked at bandwidths and so on, a number of things. Now, the last thing we wanted to look at was noise. And our common source stage looks like this, the transconductor, and then somehow there is a current source load. And so the noise of this, and I guess you've just done this now for the homework, right? So you know that's what's going on. So the key is that you can actually, we can of course calculate easily what is the total current that flows out here. So that would be 4 kT 2/3 GM. Wait a second. Yeah, GM1 plus GM2 times delta F. And then that's the total current at the output. So to get this at the input, we simply divide by the transconductance, by the gain of this amplifier, which is GM1. So this divided by GM1 squared. And then we can factor out that's 4 kT times 1 over GM1 times 1 plus GM2 over GM1 times delta F. Now here clearly this part here is from M1, which happens to be the transconductor. That's really the amplifier, right? That amplifies the signal. And that's the current source. That's the contribution from M2, the current source. So then you can go one step further and realize that the ratio of the GMs is because both transistors run the same current, it's just the inverse of the ratio of the V stars. So this is actually also equal to V1 star over V2 star, right? So from that we can conclude that in such a transconductance amplifier, at least for the simple one, and we'll see that this actually turns out to be true even for a more complicated one, we get noise from the transconductor. Well, sure, we get that, right? We build an amplifier, so we should expect to get the noise from that amplifier. There is no noise vacuum that somehow takes it away. And then we put other junk there, like this slope. Very useful, right? But it's going to add extra noise. And so one figure of merit on how good a job we did on building our amplifiers, how much noise did we add beyond the minimum that is required, right? Up to this, there is probably not much we can do, right? We can reduce this noise, but then we get rid of the amplifier. Not very interesting. So we get our job then as designers is to make that this extra term here is small, right? So if unity or less, if it's unity, then we double the noise. If it's less, well, then we sort of. And if we look at this, that apparently implies that we need to throw voltage headroom at this problem, right? In particular, it says that the V2 star should be large, and more specifically, it should be large with respect to V1 star, at least as large, or maybe if we can make it a little bit larger. Now, of course, when we design, that is evidently a compromise, because making this V2 star large means that our signal cannot be as large anymore. And because ultimately we are probably not that interested in noise, we are interested more in signal-to-noise ratio. Making V star big reduces the signal, and it also reduces the noise, but there ought to be some kind of a compromise, right? And in particular, because here the V goes down, the voltage headroom goes down with V square, right? The signal power is hit sort of with the square. The noise goes down only with V star. In practice, we can't go too far. So very often we'll actually end up with this factor being a little bit larger than unity, sometimes as large as 10 or so. And I typically call this the noise factor, NF. Now, you've seen me using this NF already before. When we then later integrate to get the total noise at the output, then generally, I mean, that NF sort of stays, and it still appears in that integral equation. Although we got to be careful, there are sometimes small modifications to it. Okay, so that's the story about noise, and this trade-off you will see in just about every amplifier. There is such an NF, and one consideration is not to make that NF too big. All right, I want to go over two things today. One of them is, basically now we want to generalize, right? So that we understand what a simple transconductor is, and we can always rely on our understanding of just a common source stage when we then design more complicated amplifiers. So now we move towards the more complicated amplifier. For that we will go over two things today. One of them is this business of differential input, and the other one we go at a more general amplifier, folded cascode, as an example and very common workhorse amplifier. So why would we rather have a differential input than just a single common mode? Well, there are a number of advantages to doing that. I know there should be a common mode feedback circuit. I just do not show it. And I just say this only for those who otherwise will accuse me of drawing things that don't work. So there are two inputs. Now, the actual DC level of these inputs is something, right? And And it can't be 0, it has to be somewhere enough to keep this current source operating, and then the threshold voltage and the V star and so on of this device, like the VGS of this device. So if we just have a common source stage, then we always had this biasing headache, these fancy but kind of stupid circuits that I showed on several slides, and how to figure out the right voltage we stick in. That problem we completely get rid of if we have a differential input. Then this voltage here and the voltage here is still a bizarre thing, but what the amplifier amplifies is the difference between these two, and so the value of the threshold voltage, for example, just drops out in this difference. This introduces then a notion of common mode voltage, and we already talked about that. If I move these terminals up and down, then at least if my amplifier is perfectly symmetrical, the current in these two branches is not going to change a whole lot if this is a good current source. And if it's symmetrical, then the small change that I'm getting is going to affect both legs similarly, and consequently I get a very good, ultimately infinite common mode rejection ratio. Incidentally, what about the noise? How much noise do I get from this current source here? Right, before we already had this one, and we just argued about how much noise it delivers. What about this current source now? Right, so very often these amplifiers are used with feedback. If we use feedback, then at least after the loop has settled, these two voltages are exactly the same. The current splits evenly here. In particular, the noise current also splits evenly here, and so we don't get any noise from this because it's attenuated by the common mode rejection ratio of the circuit. And even though the common mode rejection ratio in practical circuits usually not infinite, maybe 60 dB, right? And so this noise here is attenuated by a factor of 1,000. Starting out, it starts out being roughly the same, right? These are both current sources, so they run similar current, so they produce about the same noise. But this one affects the circuit by a factor of 1,000 less. So in practice, most of the time, we just can neglect this. But be careful if you use the amplifier open loop. Well, then depending on the setting here, you're going to push the noise this way or that way, and then the noise even becomes signal dependent, right? Careful. Okay. Now one interesting thing is how to really build this differential pair. And on the next slide, I have 3 solutions for the differential pair. So that's it. This is the solution A. This is exactly the same that is on that diagram, but the diagram's a little bit busy, so that's why. And then that runs into some kind of a load. I think there I'm actually using a resistive load. So, okay, so that's the output. So that's solution A. What's the common mode rejection ratio of this amplifier? This is the input. Well, what does it mean, common mode rejection ratio? It means that I'm moving both of the inputs up and down simultaneously by the same amount. Basically, I short them together. And how much differential signal do I develop here then? How much? What's the differential signal that appears if I move this up by 1 volt? 0, yeah. 0, right? As long as this thing is fully symmetrical. Now, in practice, it's not going to be absolutely symmetrical. Maybe there is a mismatch of 1% is not an unreasonable figure. Well, in that case, what is my common mode rejection ratio now? If I have a 1% mismatch, for example, in these 2 transistors. Now I get a common mode rejection ratio of about 1 in 100, right? Or 40 dB. That's not so great. So how can I increase my common mode rejection ratio? Well, if I move these two terminals up and down, then the current flowing here is going to change, right? Because the VGS of these devices is going to change. So how could I make it that this current doesn't change? Here, that we put resistance in here? Yeah, that would help even more with a current source, right? Right, so that's why we put this current source here. And that's also why, right, if this current source may reduce the variation of current by another factor of 100, then suddenly we have a common mode rejection ratio of 10,000 or 80 dB. Now it's starting to get interesting, right? And that's also that's the spec for, that's how we want to dimension this common mode this thing. So now the problem with this circuit. So the question is, how good common mode rejection ratio can we get with this solution B? Arbitrary? Well, ultimately we're going to be limited. Ultimately, we are going to be limited by the fact that there is also a GMB. And this GMB, the amount of current flowing in the current flowing here, ID, is going to be equal to GM times VGS, right? That's this voltage here, right? And if I increase the common voltage here, well, then the voltage here in the center tab is also going to increase. Consequently, even if I get a mismatch between the two transistors, GM1 and GM2 are not quite identical, the net difference of current flowing here is not going to be that large. Okay. But then there is also another transconductor in here, right? The body transconductor, and its current doesn't depend on VGS, but it depends on VSB, right? So here suddenly it's this voltage. How I change this voltage determines how much extra current is flowing due to this term. Well, by itself, that's not a problem, because I get that change on both sides, and so both body transconductors of both transistors are going to run the same current. But in practice, of course, they're going to be mismatched a little bit, right? 1% like before, or maybe 0.1% if you're particularly careful. So then, this one here, if I make an arbitrarily good current source here, I can make the error from the delta GM arbitrarily small also. But I cannot do the same thing for this guy here, the GMB transconductor, because it doesn't even see this current source. Making this current source better doesn't help it at all, right? So if I want to improve the situation further, if I want to get better than about 80 dB or so of common mode rejection ratio, what do I need to do? Yeah?
Maybe tie the bulk to the source?
Yeah, exactly. Right. So now VSB is, this one is 0, and now this term is gone. Okay, so now we have an answer why we want to do all. We have apparently 3 different solutions. Again, first one, no tail current source. Well, obviously we don't want that, right? Very poor common mode rejection ratio, and also frankly it's quite difficult to even control how much current is running in our amplifier. Depends on the input common mode voltage. Terrible, right? So solution A, clearly we don't want to use. Solution B, well, if we sort of are happy or content with sort of medium range common mode rejection ratio. If we want to have really excellent common mode rejection ratio, 100 dB or maybe even a little bit more, then we need solution C, where we are tying the bulk and the source together. So that's the answer to that. When I took a course like this one, it always puzzled me. There was most textbooks, they actually use this connection here. But it's used only to sort of simplify the equations because they don't want to carry around this GMB transconductor. Well, that's not a particularly good reason. The real reason is the common mode rejection ratio. In order to get good common mode rejection ratio, we need this. And of course, depending on the process, you can do this only with NMOS or only with PMOS. In fact, in our process, that NVOL process, we actually couldn't do this. We would have to use a PMOS input. So there becomes a real question, right? Do we want to do this and so on? For the 240 project, usually the answer is very easy because you are fabricating your design in SPICE, matching's perfect, and you can get arbitrary common mode rejection ratio with whatever you do. So you use an NMOS input that has higher FT, right? And you don't worry about it. Likewise, this current source here, right? Very often, it's just a simple one transistor current source. It will work that way. But again, the common mode rejection ratio is not going to be that fantastic, maybe 60 dB or so at low frequency. So a way to get around that is, so that would be a V bias 1, V bias 2, is to put a cascode. Now the common mode rejection ratio goes way up, but it sort of looks like, well, gee, now I paid a lot of voltage headroom just in making this current source there. So it's not a freebie, right? I mean, it costs something, but on the other hand, it's maybe well invested millivolts. Yes.
How important is the matching for the resistors there?
Same thing, right? If they mismatch by 1%, it doesn't matter whether the transistors or the resistor mismatch by 1%. The current splits according to the total impedance is in here. Right?
How do you compare the mismatch of the resistor and the transistor? Like, is it easier to match or harder to match for resistor?
Well, we would have to calculate this, right? I mean, resistors typically come out to be humongous, and that helps matching, right? Big means sort of we get more averaging, so the matching's better. Now, very rarely do we actually use resistors here, right? More often current sources, and then it's sort of transistors and transistors. About the same. We will. I'm not even sure whether I have it, the resistor matching data. We'll look at how to calculate stuff like that later on. Okay, so here is this busy slide. Now here I just plugged all of this stuff in, and I purposely introduced the mismatch just on the transistors here. So you see the three configurations here, and then have a plot of the common mode rejection rate. I mean, you can go and calculate this. So I mean, it depends on the mismatch that I stick in. So here we actually get out. I put in a 1% mismatch, so we get 40 dB out. And then with the tail current source, boost this to about 70 dB, and ultimately we get over 100 with the body tied to the source. Now notice also that of course we get a roll-off of at higher frequency, and that roll-off is going to occur earlier for the at lower frequency for the case where the body is tied to the bulk. Here I actually did some analysis. If you can use more zoom so that I'll go through these one by one. So these are solutions A, B, and C, right? And so so to calculate the common mode rejection ratio, I need to calculate the ratio between the differential mode gain and this ACDM that we defined last time. So the differential mode gain, of course, trivial, right? And then this ACDM, well, we've done mismatch analysis before, and we said that it's kind of difficult because very often we have to go back to the nonlinear equations because not all the parameters are available. When they are, when it's really, we can map the mismatch parameters easily to small signal parameters. It's much easier to perform the matching analysis on the small signal model. But of course that requires some insight. So here it works, so I do it this way, and in other cases I just go back to the square law model equation. So basically what I'm saying is that my input common mode voltage produces a current of delta GM that is the mismatch current flowing into the two load resistors, and that produces then a voltage delta V out at the output that is equal to this mismatch current multiplied with the average load resistor, the nominal value of the load resistor that I call R out. And then, as you pointed out, Angie pointed out, the resistor, of course, also can mismatch. And there I say, well, I use this linear superposition. Now I assume that I don't have any mismatch in my transistors, and I pump the same amount of current, VIC times GM, into both resistors, but they are mismatched by an amount delta R out that produces again a VOD. Okay, and then I just solve. So apparently a 1% mismatch in both of them together gives me 100 dB. So then the tail current source, really what it does is the current that I'm getting now is no longer delta GM times VIC, but it's only the fraction of VIC that actually produces a change in the current flowing into my diff pair. So again, if I make that a little bit, these are always tedious to analyze. So we have our tail current source here, and I apply here VIC, and I want to figure out, well, what is VOD, if you want, right? Okay, so this VIC to first order is simply appearing also here, and that produces then an ISS, right? And that ISS is incidentally is equal to VIC over RSS, where RSS is the output resistance of this current source. Okay. So now I have the same argument again as before, that this now much smaller current, right, is going to be split according to the mismatch of GM and produces an output voltage. Or alternatively, the GMs are equal, so the current splits nicely half and half, but then because the resistors are not equal value, I still get the voltage difference developing between them. Okay. And once I have done that, then the analysis is exactly the same as we've done before, and I've given the equations here. So I just plugged in some reasonable values for RSS. And finally, this is actually C, and then this one is B, where I also get the contribution from GMB. Okay. And here, actually, for simplicity in the analysis, I assume that this is the dominant contribution. Of course, it might not be. You might have transistors that have fabulous matching on GMB, and then you got to combine analysis B and C, and I guess that could be a homework, or that might even be something that I could put on the midterm, where I just want to know whether you can analyze a thing like that, right? That you can actually combine these two. Okay, so here I'm summarizing this thing. I think we pretty much said all of what's here, so you can just read this and. Yeah. So I promised that we eventually get to a real amplifier, not this common source stuff. So we'll do that now. And the amplifier that we're going to look at is a folded cascode. Folded cascode is kind of a workhorse amplifier. That's probably the most commonly used amplifier, and the one that we perhaps will start with when we have a problem, and then maybe move to a different configuration if we can't meet all the specs. I'm listing here a number of things that we are interested in when designing such an amplifier, and we'll get to these one by one, but it will take us a few weeks actually. So this is again a good summary. So when you're lost, what are we doing? Well, when we are talking about settling time, well, it's because we want to know how amplifiers settle. Huh? Okay, schematic here. Well, let me draw this again, but I'll draw it for an NMOS input, so you have both examples, and we'll talk afterwards about the comparison. So our amplifier starts with a diff pair. So these are the two inputs, right? And now, in principle, we just could load this amplifier with the current source. VDD, and actually, it's probably VSS, right? So, and there we have our amplifier, right? Now, the problem with this is the output range, which depends now on the input common mode level, right? If we bring the input common mode level way down, well, then we have a lot of leeway to pull the outputs of our amplifier down low also. But conversely, if the input common mode happens to be fairly large, then the output common mode also needs to be high, and that may is a problem in our design, right? So the folded cascode overcomes this problem by folding or mirroring somehow the differential current produced by these by the diff pair here over into another current source. So we put another set of current sources here. And actually, what I forgot here was a cascade. So let's see what happens here now is if we apply a differential voltage, then we're going to get the current delta I here, and another current minus delta I over there. Where is that current gonna go? Well, yeah, I guess I really need to introduce my cascodes here. So they shouldn't be shorted, right? That's just my... That current here sees the very high impedance of the current sources. High impedance means high resistance. It doesn't like to go there. It sees the much lower impedance of the cascode, and therefore it moves over here. So that's now the output of my amplifier, and so the current, the differential current, the differential current, the current mismatch here, produced by the differential pair, simply flows into these two nodes. Well, these two nodes see current source, and consequently produces a large voltage gain at those nodes. Now, now what is the output range here? Well, the output range depends on the biasing of this cascode on one hand, and on the mirror on the current source on the other hand. The current source here we design for whatever small v min, right? The cascode, well, we design so that this current source here still can be forward active and has a high output impedance, but basically we have here a V star or VD set and here another V star, right? So we are basically bound by about 2 VD sets or V stars here, and totally independent of the input common mode voltage. So this folded cascode solves this problem of input. The dependence of the output voltage range on input common mode voltage. And then, of course, the current sources are ultimately implemented with transistors, and that's what is shown over here. So that's the now here everything's upside down, right? Here is the tail current source. Then this is these are really the mirror current sources. That's these two transistors. Here are the cascodes, and here is the other current source. Okay? And this one, of course, has a PMOS input. The transconductance of this overall stage is simply the transconductance of the input differential pair. So it's really exactly the same thing as we had for the common source stage, right? It's still just a transconductor. But now we have all these additional devices here, so we ought to expect that something additional also shows up in the frequency response. What do you think? What is the frequency response of this going to look like? Yeah, think about it. Hey, oh. Yeah, what do you think is the frequency response of this thing? Well, what other devices contribute to frequency response? We've analyzed this circuit before. We can say this by inspection. Afterwards, you can get, they were a little bit wrong, right? A little bit approximative what you say from just looking at it. But it gives us a quick idea how the circuit is working. So how is it working? It gives yeah, but if you can use the microphone, please. Yeah.
Probably a dominant pole at the output node, the high impedance node. Maybe
Okay,
a second pole at the input.
There is a dominant pole there, yes. So, and that's set. Yeah, that's basically the same thing as we have in the common source stage. Right? The common source stage has basically the transconductor, GM, that drives into the output that gives us a unity gain bandwidth of GM over CL. Right? Or then a pole frequency that unity gain bandwidth divided by the open loop gain, right? Whatever that is. So I usually, rather than specifying what the dominant pole is, I usually prefer to specify what the unity gain bandwidth is, because otherwise I get this or out into the picture that is not so interesting. 17 mega. Well, okay, what does it mean? Okay, but are there additional poles, right? Well, in the common source stage, were there additional poles? No, there was a current source load. The current source didn't contribute an additional load, but now here, what contributes another pole? Come on. Yeah. Yeah, but please use the microphone, otherwise.
I get the drain there. We can see the 1 over GM. So
the bell.
The drain of M1 and M2, and we saw the M5. It's a
yeah, exactly. M5
GM.
and M6. They are called what? Cascodes, right? And what's the bandwidth of a cascode? FT, right? So we're going to get an additional pole in this circuit, from this circuit, that is the FT of these cascodes. Maybe a little bit lower than the FT because there is additional load hanging here in addition to the CGS. but that's what comes here. So it's really true what I'm saying. We analyze these simple circuits, and then afterwards you look at a complicated one, and we don't even get the algebra out. We look at it and we say what it does, right? That's how we design circuits, not by spending a day on analyzing this. Okay, so now next interesting question: should we have NMOS or PMOS inputs? Well, one argument goes that one argument, first of all, is whether we want to tie the bulk to the source, and then we may be constrained, right? We may be able, like in our process, we can use only PMOS devices. The other thing is, if we do this, then we have relatively fast transistors here at the input. That gives us a large unity gain bandwidth. But then we have, if these were NMOSes, in this case, we have fast transistors here, high unity gain bandwidth, and then we have the PMOS cascodes. We have a relative modest FT, and what's the problem with that? Yeah.
Can be that the second pole comes near the...
And then we get a relatively modest phase margin, right? So this solution probably ends up with better phase margin because we have the fast device here, right? So maybe we build an overall slightly slower amplifier, but then we get good phase margin. Increasingly, that's not so much a problem anymore because technologies have gotten so fast that, again, we have 5 gigahertz FT devices and we build a 200 megahertz amplifier. We perhaps can get enough phase margin no matter what, right? But that's an argument. And that is also an issue of the folded cascode design, that we have the two types of devices in our signal path. The non-dominant pole comes from one type of device, and the transconductance from the other. Okay, of course we need to bias this thing, and I've mentioned before that it's kind of tricky to set these biases accurately, especially if we have limited supply voltage. So I use one of these high voltage, high swing cascode biasing circuits, and just for completeness, I put the structure here and here. But we've gone over this, of course, the design of this. So now we need to investigate this a little bit more. We want to know what the DC gain and biases of this circuit. And for this, again, if you can use a little bit more zoom, please. Thank you. Oh, that's okay. Yeah. So I use these balloons. So when I want to know the DC gain, then I want to drive it with the differential signal. So I just drive the differential input port here. And likewise, I look then at the differential output. I also generally, when I put the circuit together, I quickly look at the DC biasing points. For example, what the current is in the different devices, right? Actually, we haven't talked about that yet, but we didn't talk about this. But generally, when I design one of these things, right, I figure out how much transconductance I need here, and I determine what V star I want to give these, and that tells me how much current I need here. So we have current I0 here and current I0 here, right? That's in order to meet my speed target. So we have 2 I0 here. Then the maximum change of current that I can produce in this diff pair is also just plus minus I0. I can, if I completely imbalance this diff pair, then one current drops to 0 and the other one goes to 2 I0. Well, for these devices here to be able to mirror or fold a current of value up to 2 I0, the current that's flowing here needs to be at least 2 I0. Right? And then in the quiescent state, when this is balanced, I therefore get the current I0 and current I0 here also. Right? That's nominally how I bias these. And then as you imbalance this, I deviate from this and develop an output voltage. So So here I just verify that that's actually the case and that I have the V stars that I like. Notice, actually, if you go and look carefully at this, you will find that this is M1. Here is the V star of M1. The V star of M1 is smaller than the other V stars. Why? Noise, right? Noise is the reason. And what's the penalty for doing that? Increased input capacitance, right? Everything comes at a cost. We need to know what it is, and then we can make the right choice. Okay. And then when I convinced myself that the circuit is working right, I go and get the gain. Yeah, that's before what. And now it's getting easy. This and we've talked about it. There are two gains. There is the differential gain, and there is the large, the small signal gain, and there is the large signal gain. So the one that usually matters here is the large signal gain, and that's this curve. Okay, so we actually get a little bit more gain than Spice would make us believe from running just a small signal analysis. But of course, if we run the small signal analysis only for VID equals VOD equals 0, then we are at this point, and that still, of course, is the maximum and a very optimistic idea. If we go down to if we change the input voltage here, the differential input voltage is just over 2 volts here, and then so here's minus 2 volts, here is plus 2 volts, so a 4 volt output range in a 3 volt supply, not too bad, right? But then our gain drops down to, well, what is this? 120. This is a gain of 120, and this gain here is well, about 240. The peak gain, but again, the peak gain, well, who cares? So if we want to increase the gain, then we have lots of ways we can increase the length of the transistors. That boosts a little bit their output impedance. But of course, then the FT of our transistors gets lower. So if we had a phase marching problem before, now we are going to have a big phase marching problem, right? We could use additional cascodes, or we could use gain boosting. Remember that amplifier that we wrap around the cascode? That would certainly help it, and that wouldn't require that we introduce bigger devices. Would that still affect our phase gain boosting? Does gain boosting affect our phase marching or not? Well, here is the cascode. Here's the other cascode. Well, if we use a gain boost amplifier, there would be then two separate ones, right? This wouldn't be connected anymore. Better not. But so the bias and then wrap it around here. So invariably we put extra capacitance on this node, and so we would get a little bit of a hit on phase marching. Again, if we have a fast technology, no problem. If it's a slow technology, then there might be an issue. Okay. So, and we could use a multi-stage amplifier. We'll look at that. We'll look at that solution also. I tried just increasing transistor sizes by a little bit, just to drive. If you can zoom in again to this. I think the biasing is the same, but instead of using minimum channel length transistors for the current sources, I use 1 micron lengths, and then the cascodes I make a little bit lower channel lengths and also a little bit lower V star, exploiting the fact again that I have fast technology, and so probably phase marching isn't all that critical, so I can afford having not absolutely highest FT devices for my cascode side. But that's sort of the thinking. Then if I'm wrong, well, I know where to, what button to, or what design parameter to change. Right? There may be other ones too. Right? So, then the gain goes up to up to 2,800, but that's from 200 some, right? But really more than an order of magnitude. We increased the channel length only by a little bit, less than a factor of 3, right? And the input diff pair we didn't change at all. So now for plus minus 2 volt, I get almost a gain of 1,000 instead of 120 before. So if we can afford it using devices that are just a little bit longer than minimal channel lengths in most processes, that will do a lot for the gain. But then if we wanted to get more than a gain of 1,000, we probably would need gain boosters or a second stage, because beyond that, now you really can, if you double the channel lengths again, then you get maybe twice the gain, or not even quite twice the gain. Right now it becomes sort of not that. You can play with this. Another important thing that is easy to forget, and then we are starting to fight windmills, is okay, so now we want to improve the gain. Let's say we decided that this isn't quite good enough yet, and so we want to do gain boosters. Well, where and how much gain boosting do we want? The point that I'm getting at is that the output impedance of our amplifier is the parallel combination of a PMOS and an NMOS current source. Their output impedances don't need to be identical. And in effect, in many technologies, it's the NMOS or the PMOS. One or the other device that actually has much better output impedance. Very often the PMOS just does better than the NMOS. Or here actually it's the other way around. And so we want to know that. We need to know that. And I keep putting this away. So that's why, if you look, you don't need to change the zoom. That's why I put in my schematic in such a bizarre way. I do not short, right? I mean, this is the output of my amplifier. I do not just tie these together, but I actually bring out 4 individual terminals, my amplifier. Most of the time, I just tie those together, right? But when I want to know what I need to do in order to increase the gain of my circuit, I go and force a current into the NMOS and force into the NMOS, and I force a current into the PMOS, do a small signal analysis to measure the output impedance here as a function, presumably, of the output DC output voltage, the bias. The output voltage now becomes the bias point in my measurement here, and then I get a picture that looks something like this, right? Where this is the total output impedance. It's going to look totally symmetrical. I can't say anything whether it could be the PMOS has infinite output impedance, all the NMOS fault that we don't get infinite gain, right? But I can't see this from the combination. In that case, of course, I would have to improve the NMOS only, and so here I get the output impedance just of the PMOS branch and the NMOS branch, and here I can see that, well, they're actually not so poorly matched, but the NMOS has a little bit higher output impedance. And so you will actually frequently see amplifiers published where the NMOS or the PMOS, where one of the current sources uses boosters, but the other one doesn't. And that designer went through this exercise, plotted this, and said, well, gee, I mean, I don't need the gain booster for that guy, I need it for the other one. Okay? Important. I also show you a bunch of test circuits. There's nothing too fundamental about them, except that those are not the common simulations that you do. I mean, they are not in every undergraduate textbook. But when you really design a high-performance amplifier, then you want to know these things. First, we want to know, of course, how we designed for GM, right? And then we go and figure out what the bandwidth is of our monster amplifier, and we find that it's short, right? Well, there are lots of possible reasons. One of them is that GM could be smaller than we actually had designed for whatever reason. But then we go and track down that reason. But if we don't even know what GM is, right? We only know what we think it ought to be. we may run around in the dark for a while. Same thing, the output capacitance, right? Big pain in the neck. I mean, of course, there is a load capacitor there, and we made it just large enough that it's 2 picofarad. We know that, but there is also the junction capacitors, the junction of the switches and other stuff hanging there. Well, how much really does it add? It's difficult to get that. The easiest thing is to simply measure it, and for that, again, what we do is we drive the output. In this simulation, we drive the output of the amplifier, and we look what current flows into it. And the ratio of voltage over current, well, is impedance, right? Or current over voltage is capacitance, if we also divide by frequency. So here is the output transconductance, right? So I forgot. I guess I could have looked at really what I designed for and came out with something, right? And also, of course, the transconductance rolls down because the transconductance is simply the slope of current, differential current that flows into the output, right, that I short circuit in this case, and as the slope drops, so does the GM, right? I can measure the differential output capacity I just mentioned. So I also see over which range it's actually capacitive or not. Right? At very low frequency, of course, it doesn't look very capacitive because I have the R out. That, after all, is finite. And then at high enough frequency, the amplifier sort of gives up its ghost, and the capacitance dominates. About half a picofarad, almost 600 femtofarads hanging there on this amplifier. We have to look at the devices, but certainly not to ignore, right? Same thing, differential input capacitance. Here we see the Miller effect, right? At low frequency, we get Miller effect that increases the differential input capacitance, and then higher frequency that drops away. Finally, the bandwidth. So here I get the gain, and the gain is here 70 dB, so that would be almost 4,000 or so. Well, about 3,000, right? Which is what we said that we get for when the amplifier input and consequently output are just at 0 volts. VOD equals VID equals 0 volts. So this is kind of, it comes out of SPICE, but it's not very interesting. And certainly don't use this as the gain of your amplifier, even though your undergraduate text tells you to do precisely that, right? But beyond that, then somewhere here, we can't even see it on this scale. Somewhere here, probably a little bit higher frequency, we get an additional pole. We know now that's the cascode, right? And because of that, we get the finite phase margin. Now that's interesting, right? This unity gain frequency, 300 some megahertz, and the phase margin of here 75 dB, not too bad, right? Now you can design it again with NMOS inputs, and you may well end up with 65 or something like that. Okay. Now this business, of course, sort of cries for feedback. Right? This amplifier here looks interesting, has a high gain and so on, but as is, it's almost useless. Right? We need to apply feedback so that we can get a bandwidth of not 100 kilohertz here, but the bandwidth of a few hundred megahertz, right? And the gain of maybe 2 or 4 or whatever that is precise and doesn't vary all over the place. Okay. So most books and most courses on circuits, and this is no exception, has a special chapter on feedback, and you discuss feedback. Why? Why does feedback deserve such special attention? In particular, why? Usually when we analyze feedback circuits, we use some special techniques, math, right? 2 ports and loop gains or return ratio analysis. So why do we do that? What is the key, compelling, most important reason why we need to do such special analysis when we have a feedback circuit? What is so what is so critical about feedback that we need to? I mean, there is obviously all these benefits that we get, right? We broadband the circuit, we set the stable gain, and so on. Clear, right? But that usually takes about 2 pages. Then what is all the rest?
Maybe stability?
Yeah, exactly, stability. That's the main thing, right? There is all sorts of other stuff that usually hangs in these chapters, like clever ways on how to calculate input and output impedances of circuits with feedback that take less time than maybe using straightforward nodal analysis. That's not so special, because we always can go back and analyze, even if it's got feedback a circuit, we can analyze it just with straightforward nodal analysis. There's nothing special to it. But if we just do that, we know nothing about stability. And so the key about any feedback chapter must be that it figures out precisely and clearly how to analyze a circuit with respect to its stability. That is particularly important because it's not easy to do. And in particular, most designers have no clue on how to figure out reliably whether a circuit is stable or not using SPICE. Okay, so for stability, I listed here sort of ways on how stability is even defined. Sometimes it's defined as bounded input, bounded output. Well, that sort of implies that we know what the input is, but it could be that we test with sinusoids and it's stable, and with square wave it's not, right? So really this definition almost doesn't help. Linear system, well, that is a first gross approximation, right? We have this terribly nonlinear thing. We've seen that the transconductance varies all over the place, right, as in a function of input bias. Right? So the first thing we do when we linearize our circuit, and then we establish the stability of that. We're going to do that here also. But we need to be aware that, heck, we analyzed the stability of a circuit that we just plain didn't build, right? We built something different. And so perhaps we can convince ourselves and we can ensure that the actual circuit that we design is also stable despite that it's different. But we need to think about it. And I can give you circuits, nastily enough, but they're good circuits, where you can do this linear system analysis, and lo and behold, it's stable, and then in reality it's not, because it's a nonlinear circuit. Class AB amplifier, typical case. Or circuits that need to be powered up, right? Because during the power on transient, it goes through all sorts of states. It can start ringing long before it reaches the steady state, and it will never come on the way you'd like it. Okay. So in a linear system, at least the definition of stability becomes fairly simple. If all the poles are in the left half plane, then the system is stable. For example, in the context of bounded input, bounded output, there are some clever tools like the Nyquist criterion, or a more special case, the Bode criterion, like this phase margin, reading on the page before. Now, in this sort of lecture, we go look at how to analyze feedback using hand analysis, and then also how to do that with SPICE, okay, and what the pitfalls are doing that. Okay. So first of all, this is nothing profound here. General feedback circuit, right, has a forward gain that is not very well known, and it has a feedback gain that is very precisely known and probably very linear, and so on and so forth. And the idea, of course, is that the characteristics from here to here, they're totally determined by this feedback thing. And that goes through the normal analysis. I define first the loop gain. That's the product of these two gains here, right? That is, so here 1000 times 0.25 would be 250. And then if this loop gain is very large, the overall gain is 1 over f. So electronic feedback, and we saw that already in the context of noise, usually doesn't use that ideal feedback concept. But the first thing is that there are often parts of the circuit that are not really part of the feedback loop, like this resistor, but sort of help us determine the gain. We've gone through this also. And then we have that the gain is not equal to 1 over f. Just another reminder. Okay, so now it gets more important. So this is again very simple. But stability depends on the loop gain. So that's the gain measured around the feedback loop, right? In particular, stability does not depend on A of S. It does not depend on the gain just of the feed-forward gain. Of course, that is part of T of S. But by just knowing this gain here, we cannot really be sure whether the amplifier is stable or not. I mean, we could actually have a circuit that is unstable if we just were to put feedback around, unity gain feedback or so, around just this part, would be unstable. But if we use just the right feedback network, it becomes stable. And then, of course, more often the other way around also. So this analysis here and specifying a unity gain a phase margin of 75 some degrees, that is for a very, very special case, namely that the feedback factor was unity, right? So implicitly, because I picked this up at unity gain, I implicitly assumed here that somehow I put the unity gain feedback around this amplifier. That is very practical. First of all, most amplifiers you buy off the shelf, they are compensated to be unity gain stable. Why? Well, because people figure that if you go and use the amplifier, you probably don't want to make it an attenuator or so, or actually, how could you even, right? So if it's stable for unity gain, it probably will be also stable in your case where you want to have a gain of 5 or so, right? But you got to be careful. It's not necessarily stable then in all situations. For example, yeah, well, I can actually use this, right? This circuit here, it doesn't quite have unity gain, but it has a gain of perhaps less than unity, or if these two resist, but if I add some capacitance here, and I get it just from the amplifier, then of course I'm getting a pole and an additional pole, and so if these resistors are of sufficiently high value, that pole may be a significant additional non-dominant pole. So now I have the dominant pole that probably comes from the output if this is a transconductor. I have the non-dominant pole or cascode here, and I have yet one more non-dominant pole. Well, depending on where they are, two non-dominant poles is a little bit a lot, right? And this may then go unstable. So unity gain stability is sort of a worst case, but not really. So important thing that the stability analysis really relies on figuring out where the poles are of T of S. Okay. And so consequently, if we want to establish whether a circuit is stable or not, a linear circuit is stable or not, then we got to figure out what is T of S. And that's hard. Well, let's look at it, how we do that. So here is a simple circuit example where we do that, right? So we have again, I did that again, right? Instead of putting the whole folded cascode amplifier in here and getting lost in lots of individual bits and pieces, I just I go back to the common source amplifier and say, well, we sort of take the results from the different pieces. So we said that we really analyze the stability of the linear circuit. So I draw the small signal equivalent. And now I want to know the loop gain of this thing. Well, for measuring the loop gain, what I need to do is I need to somewhere open my loop, insert a test signal, look on the other side of the loop that is now open, look how much comes out, and the ratio of what I put in and what comes out, or the inverse of that, is my loop gain. Right? That's what I want to do. But breaking the loop isn't all that easy. If, for example, I break my loop here, why not, right? Well, the trouble is that before I had broken the loop, my amplifier also was loaded by C2 and all of the stuff that was hanging here, right? By opening the loop here, I suddenly changed the load on our amplifier. Heck, and that probably changes its frequency response. And consequently, I'm measuring now a circuit that really I didn't build, right? So I need to find a point where I can break the loop, which doesn't change at all the characteristics of the loop. And that's in general when in a place where I have a source, a controlled source in particular, right? Like this one here. If I break the loop here, that's okay because that's an ideal current source. It's not ideal really because the other part here is its finite output resistance, but I put that on the other side of the breaking point, and I can do that because of my model, right? So this part really is an ideal current source, and the current flowing out of this current source doesn't depend at all on how I load it. It puts out its current because it's ideal, right? So that's what's done in the next slide here. I broke my feedback loop, and I now figure out what the current is flowing out of my ideal current source. Conveniently, I short this current source. It doesn't really matter what I do with it, right? Because it's ideal. I could leave it open, and somehow an ideal current source still manages to run the current through an open circuit. Then I drive the now open output with a test signal that now flows into our out and so on and produces a voltage here that ultimately then gets turned in a current over there, right? And then the ratio of these two is my loop gain. And that's what I've done over here. So I get one pole from this node, and this is just a voltage divider, gives me no pole. Okay. It's tedious, much like noise analysis. It's tedious, right, to do all these calculations, but there is really nothing particularly profound about it or difficult about it. We just got to do this. The difficulty comes in when you want to do this with SPICE. SPICE is very convenient, right? We never hack a small signal model into SPICE. We put an entire transistor into SPICE, and then SPICE kind of internally draws the small signal model for us. But the challenge with that is that this node here is no longer accessible. I mean, it exists deep down somewhere in the simulator, but it's not accessible for us. And so how can we break the loop there? So this works well for hand analysis. That's where we use it, but it doesn't work for SPICE. So this basically shows this again. Right? I mean, that's what happens inside SPICE. And yes, I mean, these nodes are present. We could break the loop here or here, but there is no. Actually, there are more modern, more recent versions of SPICE that actually allow you. They give you a scissor command and they cuts there. So what do we do instead? Well, one popular solution is shown here. So we need to break the loop. Well, one problem with breaking the loop with SPICE is that the bias point depends, of course, on the loop being closed. The minute we open the loop, but the transistors are no longer biased correctly, and then SPICE will not calculate the correct small signal model. So a way to get around that is to not quite open the loop, but sort of. So we put a really huge resistor in the feedback loop. This is almost an open, and so now we kind of treat this as the input and this as the output. Now, how do we stick the input here? Well, we don't really want to disturb the DC bias point, but we want to get our AC test signal in. So we put the input in through an AC coupling transistor at capacitor. And again, I mean, this is only a crutch to do our simulation, right? You've never done this? Did you ever build a circuit with feedback? You gotta be You got to be worried. You didn't test it. Okay, and then the next problem we have is that before we sort of opened the loop here, we saw, of course, the CGS of this transistor here, whatever it was, right? Or the input capacitance of the amplifier, right? Now that's no longer here, and consequently, probably our circuit is actually more, well, whatever. The stability of our circuit anyways changed. So we put here some kind of a mock load, and the mock load, maybe just a transistor of similar size or so that we are hanging here in addition. So we're kind of duplicating parts of our circuit, and we pray a little bit and hope that it's not too far from reality. And yeah, but you never did this? Yeah, you don't do that.
It seems that sometimes the operating points are so off that it sometimes just what's supposed to oscillate doesn't oscillate, etc.
Well, I mean, you gotta do your you have to when you do this analysis, you have to make absolutely sure that the DC, the operating point of your analysis and the operating point of the actual circuit, how you use it, they are exactly the same. Because otherwise, the GM, if this voltage here is 50 millivolts lower, the GM of this device is going to be way lower, right? And it's just irrelevant. I mean, what stability result comes out of this analysis is just totally irrelevant, right? So anyways, this circuit, it's a crutch. And if you're diligent and careful and so on, we might be able to get a pretty good answer as to whether our circuit is stable or not out of this. But there is still a little bit of praying at least involved and experience, and I don't know what. I mean, I don't recommend it. You have a better idea? Well, in that case, come Thursday. We'll talk about it.
But I look at the solution because when I asked you, because I have a different GM, because there was too many parameters on the and yes, because in the solution you use the GM and calculate the current. Instead I
actually even put two different solutions up because I said in the solution, look, there are really two ways. The problem can't be done as is, but there are two reasonable ways.
Because this is RMS.
Yeah, I mean, I don't know why even he said that. I mean,
just
noise
point,
voltage.
so it's not just to.
Yeah, just well, maybe I take it along and I'll if that's okay. Or otherwise, you send me or Manu. It's maybe even better if you send.
It's not a problem.
Send an email and then.
Because
yeah. No, we'll give you the pointers. No. Oh, you're early.
You're right, I am early. I was thinking I was late. I was with some people and I was trying to get away because I was afraid I'd be late. And it became a mental perception.
Yeah.
So you're right.
10 minutes to running on kind of.
So how's your class going?
Oh, it's going okay. Everybody falls asleep. You have no problem.
Yeah, this room is so. I had a